All right. So just one little thing I just want to finish up from last week. Last week we talked about electric field strength. Right? We talked about electric field strength. We talked about Ohm's law. Right? We looked at Ohm's law. Start finding electric field strength. Hey, Ranzo, some faster. Right? We looked at finding electric field strength. And today, we just quickly want to go through electric potential. All right? So electric potential, you kind of know it already. You kind of see the quantity already, right? But the electric potential at the point in an electric field is defined as the work done per unit charge, right? Electric potential carries the symbol V. Carries the symbol V, and V is equal to W on Q, right? Work done in moving unit charge, right? From infinity to some point. You might remember this formula. Electrical energy is V by Q, right? Same principle, right? V is the electric potential, W is the electrical energy, and Q is the charge. SI unit, same SI unit, capital B, that's volts, right? And you have a definition there. Right, the Panchu, we can also explain or define electric potential into the Coulomb's law. V is equal to Q over 4 pi epsilon R. Right? My small question is how come? Where that come from, Panchu? Where that V is equal to Q over 4 pi epsilon come from? Start from here, right? W is equal to, right? W is equal to, you're going back in circle. W is what? Okay. So if I use this here, W is work, right? Work is what? Energy is what? Force by distance, right? That's why it's an R. That's okay? All over Q. What is force again? What's the force between two charges? Let's go down again. The force between two charges separated by distance R. Coulomb's law from last day. I see what I can think of. Yeah, yeah. So we end up with the law of Matada. Right, so right, so we know that V is equal to W on Q. We said that V is equal to force by the distance moved, right? This F here is some Coulomb's, right? Coulomb's law, right? So Q, I'm using capital Q and lowercase q, right? Over 4 pi epsilon by R squared. I'm multiplying it by R, and then this whole thing I'm dividing it by Q. This R will cancel, and I will get V is equal to Q by small q all over 4 pi epsilon R. This divide becomes multiplied. This Q becomes 1 over Q. Q will cancel, and I will get the formula that I just showed you all. Q over 4 pi epsilon R. That's okay? So if I ask you to find electric potential, this is your electric potential. No, I just changed, instead of using Q1 and Q2, I use big Q and small q. That's all. That's okay? So instead of using Q1 and Q2, I use big Q and small Q. Right? Basically, I'm just trying to show you that one of the Q cancel out. Right? So if I ask you to find electric potential, that's all it will do. Right? And this is the most important thing about electric potential. Let me see if anybody else reading ahead. What type of quantity is electric potential? Huh? Huh? Wrong. Right? It's a scalar quantity. Right? If you remember from last week, electric field strength and force, they were two vector quantities. So everything we did had to do with getting through the sign, right? And direction. All right, so watch this here. Suppose I wanted to find the electric potential at the point A. Right? How do I find the electric potential at the point A? First thing I do, I find the electric potential due to Q1, right? So that will be Q1 over 4 pi epsilon R1, right? And then I find it due to Q2, so that's minus Q2 all over 4 pi epsilon R2, and just add the values. The reason I included the sign is because it don't matter. Direction don't matter. I just taken the sign of the charge, right? The reason the direction doesn't matter is because V is a scalar quantity. So I don't have to worry about sign. I mean direction. Okay? So if this charge is positive, it doesn't matter what direction the electric potential in, just work out the value. If this sign negative, it doesn't matter direction, use the negative charge and work it out. Then add them up. Right, Anthony? That's all we're doing. The reason for this is that it's a scalar quantity and direction doesn't matter. Okay, just make a note of that, please. All right, so I was just I just wanted to wrap up that from last week, right? All right, so today we want to focus on something called capacitance, right? Right, yeah. But if it was two positive, it's still added. If two negative, it's still added. Yeah, always adding the values there. Right? And in 99, so the sign doesn't indicate direction. Sign is just what charge is going. Okay? The sign doesn't indicate the direction that you're doing it. Right? The sign only indicates the type of charge it is. All right. So today I want to start with capacitance. I'm going to tell you, I am going to send you all a different set of notes, similar thing, but I just change it up a little bit based on the objectives. Who? It's been 4 years. 4 years, 4 years. Shall you have 2 hearts on the end? Yeah. So how come have your name saved then? And you're not in English. Huh? All right, let's go. Right, so I'm still trying something. You will see those small mistakes, but like add your name and them kind of things, right? But I ain't reached there. Right. Right, so these notes should be a little more, should be formatted a little bit better. I didn't really figure out how to do some diagrams as yet, right? But you know it's nice. Right. These notes here are based on every objective. Okay, you go back to your syllabus and you divide that way. And make the notes according to the objective. Okay, so now we're going to focus on a new, can't talk about it already, but we're going to take a look at a new component called a capacitor. Right? It's something that is used to store charge. That's okay. I sent you this note so you don't have to write. Okay. Let's just focus here and make sure we understand everything. Right? So the capacitor basically has the ability of storing charge. If you ever saw a capacitor before in the lab, you'll recognize that the SI unit is what? Farads. Capital F. Farads. Yeah. Farads. Right? So the unit is of farad. So we are going to take a look at this new quantity, the SI unit. We're going to take a look at some calculations using it. After that, we're going to talk about, well, what it's made up of, right? So I'm talking please. Right, first thing first. Right, I just do this so if you see any mistakes, you'll let me know, right? So the capacitance C is a measure of a capacitor's ability to store charge. So what does a capacitor do, Shivish? Right, stores charge, right? The larger the capacitor, of course, the more charge you can hold, right? Right, so the larger the capacitor, the more charge the capacitor can store for a given voltage across the plates, right? So it appears that capacitance is dependent on 2 quantities. What are they? Charge and voltage. That's okay? Malia is dependent on what 2 quantities? Charge and voltage. And you will see that, capacitance is charge over voltage, if you like. Let's talk about this. Right? So capacitance is charge over voltage. Are you okay with that? So our first thing here is how do we define the farad? Real simple. You remember I told you what to do? Like if you have to define 1 farad, all you have to do is put a 1 for each quantity in the formula. So 1 farad is 1 coulomb per unit volts. That's all. That's okay. But the more formal thing is the unit of capacitance is farad. A capacitor has a capacitance of 1 farad if a charge of 1 coulomb increases the PD across the capacitor by 1 volt. Right? So as you store charge, a voltage builds up. That makes sense? Charge is what? Charge is electrons, right? Negative charges. So if something have no charge and it starts to build up with electrons, what will happen? One side will be more negative and the next side will become, and the difference between positive and negative is a potential difference. Are you okay with that? You okay with that? That's the way the capacitor works. Right? It will store that charge, and by storing the charge to power, right, it will be building up. It will be building up potential difference. Are you okay with that? Deviation. Are you listening? What's the next deviation? Right? Sorry. Right? In practice, the farad is too large. Right? So you'll probably never see a capacitor with not never. I think Elon Musk, someone will charge it real big. Well, you can take a look at that, right? Take a look at those chargers from what do you call them again? Not Elon Musk. Tesla. You'll see how big those capacitors are. Right? But generally, in practice, the farad is deviation. What's your name? Deviation. Right? So in practice, the farad is a large unit. So capacitors typically have values in smaller units. Micro. I have a capacitor somewhere here. Normal 10. Normal 10. Right? So microfarads, nanofarads, and picofarads, you will more see in the lab microfarads, right? Come on, closer now. And I just send it to you on the group, you can open it up. Right? A capacitor stores a charge of 3 coulombs when connected to a 3 volt. What is the capacitance? Very easy, right? You divide the charge by the voltage. That's okay? And you get a value of 1. Well, basic stuff, right? But let's show you how to use the formula. Right, next. What's our real world applications of the farad? Capacitors with capacitance measured in farads are used in special applications such as supercapacitors and tuning circuits. Supercapacitors are used for energy storage in applications where rapid charging and discharging are important, such as in regenerative braking systems in vehicles. All right. So we use it here as supercapacitors, right? In tuning circuits, small capacitors measured in pico and nano are used in circuits like radios, televisions, or tuning to the frequency. Anybody remember when we used a capacitor again? Just the other day, about 3 classes ago. Anybody can say it. How you spell it? I just say it in our what's the name of it? a rectifier, right? Right? In the rectifier bridge circuit, had a capacitor, and that was used for what? It was used to smooth out the full wave rectification, right? So Raya, what was the capacitor used for? Right? So that's the way, that's how we use it, right? Online, are you okay there? Huh? Right, Anthony, are you okay there? Kyra? Alright, so here we have a small example, a small example, and we have a 5 microfarad capacitor. A 5 microfarad capacitor, it gives you the voltage to find the charge. The one formula we have for the day, we just use it now. One formula. That's okay? Right? Q1 B, we arrange it and then you find for Q. Are you okay with that? Are you with Mr. Right? Panaya? You sure? Everybody okay with that, right? Right, so that's basically that is basically a full subjective was it farad, and it gives you a small idea from application, right? The next thing we have to learn is to be able to use Q and B to solve problems, right? But if you know what Q is, and we know what C and P is, everybody okay with that? Yeah, you okay with those two quantities, right? All right, nice. And I just show you there how to manipulate it with those who buy that subject at the formula, right? Excuse me. How you find B? Should we are here? Pay attention, right? So B is equal to Q1C. That's all right? Right? So we're here. Right, to my favor, you can calculate that charge real quick. You can do the calculator, you don't have to write. So want to write, go ahead. In your notes, solution there. Yeah, work out after my please. 10 microfarads, 9-volt battery. I was going to put this in a box. I'll put it next. 90. Work it out, tell me what's the charge being stored. There you working it out. How much you got? 9 by 10 to the minus 5, which is how much? Which is how much micro? 90 micro, right? So we have to learn to do that, right? We have to learn to take the value. I'm gonna show you that in case you never do that for your life. Take the value 10 by 10 to the minus 5 coulombs and convert to a prefix that we know. Okay? So if I have to convert to minus 6, means this will have to go to 90 by 10 to the minus. Okay? So that's how they got this, right? Next quick example, find the voltage, please. Find the voltage. If you don't mind, you can find the voltage, please. Without the word trouble, little trouble. Good trouble, leave it. No, I'll read it. Just put it. Everything I just changed. Right, since I nobody else. Right? What's all got here? 10 volts? 10 volts? Give it up. Nice. Right? Real world application. The relationship is used, right, in designing electronic circuits, particularly in filtering and right in filtering and energy storage application, and you have two basic applications there. Think you know already, right? Right. We have three basic questions. Try them first. Do you want to write it? You don't have the answer for this one. Try them first. Yeah, we'll pick out. Okay, no, let's move on. No, see, I'm like. Okay, right. You have any question? Yes, yeah. Pardon me? C is capacitance in the air in power. Right, take your time, we'll come out. Nothing difficult as yet. I can hear. I can. Yeah, I want to follow the book. You want to just put what the rules on you. All right. So let's see if we can work these out, right? So a 4 microfarad capacitor, they give you the voltage, they give you the capacitance, they want to define charge. Right? So we of course we know C is equal to Q1V, Q is equal to C by V. So that's 4 by 10 to the minus 6 multiplied by 12. So that's 48 microcoulombs. Are you okay with that? Yeah, 48 micro, right? Number 2, they give you a capacitance and they give you a voltage. Sorry, they give you a charge, my bad. So the capacitance is Q1B. That's 150 by 10 to the minus 6 all over 30. And I got 5 microfarads, yeah? Yeah. Yeah.
No, that
Same thing, I just went micro.
yeah, when you have the micro,
Number 3, they want the voltage. We know that voltage is equal to Q over C. Right? What voltage is needed for 75 microcapacitor? Sorry, yeah, microcoulomb, sorry, of charge 25 microfarads. So both of them is micro, right? So that's 25 over 75. Right? 0.33 volts. That's okay? So we're just manipulating this. Yeah. What did I write? Back to front. Q is Q is 75. Oh yeah, sorry. Sorry about that. Q is 75 over 25. I didn't write in mine too because it cancel off, right? I didn't write in my crew because it cancel off. So the answer is 3. Okay? Are you okay with that? Isham, you work it out? How much you get? Isham, you did not work it out. Right. So next, taking a look at how to find capacitance again, but we're looking at the things that make up the capacitor. Right? So we're going to find capacitance using the quantities that make it up. Right? Problem is I couldn't really draw it. So watch this here. A capacitor, real simple, right? It's 2 plates connected to a circuit and something called a dielectric in the middle. Right? That's all. Right? It has 2 plates, that's 2 conducting plates, and some dielectric in the middle, air. Right? There are different types of dielectric, but for now we're air. We have a dielectric in the middle, 2 parallel plates connected to a circuit. The symbol, real simple. Right, Anthony? That's the symbol for capacitor, right? Okay with that? Right. We can also find the capacitance of that capacitor by looking at 4 sometimes, right? The first quantity is the area of the plates, right? The second quantity is the separation between them, D. Right? The second is the separation between them, Z. Right? And the next one is based on the material in the middle, based on the dielectric in the middle. Right? So it's dependent on D, separation between the plates, A, right? The area of the plates, and it's dependent on the dielectrics and the permittivity of the dielectrics. All right? So let's see what all this means. The capacitance of a capacitor can be increased by placing a dielectric material between the plates. So here's what it's saying, right? If we have the plates and we change the dielectric in the middle here, we will be able to adjust the capacitance value, right? The dielectric is dependent on those 2 values there. Okay? Right? And the capacitance of a capacitor can be increased by placing a dielectric material between its plates. A dielectric, right, is an insulating material that reduces the electric field between the plates, allowing the capacitor to store more charge for a given voltage. Okay? So as I said, remember we talked earlier about how the capacitor really works. As charge flows into the plate, it stores that charge. The more charge it can store, the better the capacitor. Right? How does the dielectric help do that? Anyway, that highlights it there, right? But the dielectric is an insulator, right? So because it's an insulator, it has the ability of reducing the electric field, right? But by the way, what is electric field? I just find the electric field strength. Is equal to. So what do you think the dielectric is really doing? Look at the formula, F1Q. What do you think the dielectric is doing to make the E value smaller? Look at the formula, right? That's all. It's either increasing the charge or dropping the force. And the more charge dielectric allowed to be stored, what will happen? The smaller the electric field. You're saying that? So remember the dielectric is an insulator. That's okay. So what it will do, it will allow the material inside to store more charge, and by storing more charge, drop the electric field. Okay. So please remember the things from last day, right? The capacitor, C of a capacitor with a dielectric is given by that formula there. Right? Very important. I am understand what all the things are. Alright, epsilon is the permittivity of free space. Epsilon R is the relative permittivity of the material. So what they do is they compare the permittivity with air. Right? You remember like relative density, right? You compare it to a substance. Here we compare it to air. So Nalia, what do you think this value will be if I had air in the middle here? Who said that? Yes, the answer is 1.
Okay.
Right? Because you're comparing it to air. That's okay? Suppose it was comparing either to something 4 times greater permittivity than air. What would epsilon R be? 4. Right? So in some textbooks, you might not see epsilon R because in Nikolai, they assume epsilon R is 1. Okay? But ideally, this is the formula. Right? Ideally, that is your formula there. Alright? So if I ask you to find capacitance area, what are the 2 ways that you can find capacitance? If I ask you to find the capacitance of a capacitor, there are 2 ways you can do it. Q1V and the formula that's in our C then. Epsilon, right? Epsilon naught, epsilon R by A all over D. Right? Because suppose I made the plates larger in a capacitor. What will I do to the capacitor? The C value. Sure. And what would happen if I make the D value smaller? I bring the plates closer together. You'll make it smaller. Sure. Right, correct. Right, you'll make the C value. Wait, that? No, that's wrong because if D smaller, C value will be larger. Okay, test me there. All right, nice. Everybody okay with that? No, that's not good. You have no right to do it, just listen. Right, the effect of dielectrics on the capacitance. The dielectric constant, epsilon R, is a measure of how much a material increases the capacitance when compared to a vacuum. For example, air to a vacuum is 1, water and so on, right? But you have to learn those values, they'll give you that, right? They'll give you all the constants. Adding a dielectric increases the capacitance because the dielectric reduces the electric field, which allows the capacitor to store more charge for the same voltage, right? Just do me a favor, calculate that number, please. You don't have to write it, just put it in the calculator, right? You want to work it out, go right ahead. Calculate that C value there. Please show me the calculator. Use my calculator. And your pen?
It's 8.85 by 10 to the minus 12.
8.85 by 10 to the minus 12. Very good. So I can start.
So we see.
Perpendicular. No. Perpendicular. I shall see there. Wait, it's this Saturday, right? No, that's Wednesday.
Yeah, some mediates, some.
No, it's Saturday. I'll fix that. Right, so we know the area. Yeah. We know the area. What? Oh. Right, we know the area. We know epsilon R is 5, we know epsilon naught, and we know D. When you work it out, 8.85 by 10 to the minus 10 farad. You okay with that? Let's try 1 and 2 fast. 1 and 2 quickly. Online, are you okay there? Skyra, are you okay, Mariah? Yeah, you get it too. Right, let's try it 3 here. Yes. How can I help you? Right? Okay, that.
Justin, have you got the answer?
How does the capacitor of a capacitor? What's be linked to the first one? Sorry. Huh? The second one linked to the first one. No. Still one something different. Sorry about that. How does the capacitor chain if it dielectric with a constant of signals inserted between the plates? So what will happen? If instead of 4, supposed to be 8. Right, I made a little mistake. Supposed to be 8. Not 6. Right, but technically it's supposed to be 8, right? So number 2, how does the capacitor change if the dielectric is now 8? It was 4 before. So the capacitance is double.
Yeah.
That's okay?
Let's say this is
No, if it dielectric with a constant of 6 is inserted instead of 4. Instead of 4, yeah. Sorry about that. I put some merges together and so on. Number 3, try that fast. Vinay, try number 3. Huh? I was changing the number 2. Think about it. Just think about write down what you have. Write down what you have, see what changing, it might help you. What's all got for number 1?
8.85 by 10 to the minus 10.
8.85 by 10 to the minus 10. Again?
Yeah.
Well, so we change it to be 70.7.
Huh?
Okay.
Right, yeah, this is supposed to be 8 because I want this to tell me that it's double. Yeah? Yeah, by itself.
Oh, sweet.
Now, number 2 by itself. So they give you the original capacitance and they give you the new permittivity. What will be the new capacitance? Shivari, no working on anything? Which one? Huh? Huh? Try something? I'll show you that one.
That's the tira, acho que também já fiz isso.
You don't have to involve.
Huh? Huh? 15? Ready?
Yeah,
Ready?
yeah.
Shirish. Go out. Bring it fun. Bring it number one. Right. So in order for us to find C, watch this here, right? In order for us to find the capacitance, we need mu naught, we need mu r, we need A, and we need T.
Yeah.
That's okay?
We have you.
Right? So as I said, we know we have mu r. So the capacitance is equal to mu naught A on D multiplied by 3. That's okay?
Yeah.
So because we know this alone. That's all we know. All the other things we don't know. All right?
We don't see first.
Well, we can, yeah, no, I'm talking about for the new one. For the new, this is for the new. Right? We know it's 3 by this value here. Right? So for the last one, for the old capacitor, we know that C is equal to mu naught mu r A on T, same formula. We know here is 10 microcoulombs, sorry, microfarads. Epsilon naught, you can always find out. Epsilon naught by E all over D by epsilon r. I just kind of rearrange the formula a little bit, right? Right. So right, so epsilon A on D, I'm moving it across here, and I will get epsilon A on D is equal to 10 mu F all over epsilon R. You're seeing that? So now, if I take this value here, and I substitute in here, okay, see what I did right. All right. Right? I forgot to write it down. All right, what you said. I'm gonna show you what I was supposed to write. I think we'll get out the numbers. Right, sorry then. Right, the old capacitance was 10 microfarads, right? And you had to get a new capacitance. You had to get a new capacitance given that this new value was supposed to be 3 mu r. So that's 3 times the old one. Right? So I was supposed to put mu r on the end there. Right? I just put 3. Sorry. Right? So it means that mu n is equal to mu. I keep putting mu, I mean epsilon, right? Right? So the new value will be epsilon naught by epsilon r multiplied by the area all over D. That's a new value, right? We know that this epsilon value is 3 times the old epsilon value all over D. So I can factor the 3 on the outside. So I'll end up with 3 epsilon RA all over D. And this here is from the old one. So it will be 3 by 10 microfarads, which is what you all were saying, 30 microfarads. So I was supposed to put in mu r at the end, sorry. Okay. So the new epsilon, the new permittivity was 3 times the old one. Right? So I left out the last thing. That question mark is supposed to be mu r. Okay? So that's the way I wrote it out. Sorry. All right, so in short, today we learned about two ways that we can find capacitance. Right? We learned about finding capacitance like this, Q and V, and we learned that formula there, epsilon naught, epsilon R, A, all over T. Right? But what will happen if you put capacitance in series and parallel now? What will happen?
Yeah, more complicated.
So let's start with series. Right? I will do series here, and then somebody will come and do one in parallel. For me. Right? So copy that down, right? Sorry about that, right? There's supposed to be a mu R at the end of that note, right? Right? There's something I just want to just go over quick. Help me out here. Well, if I have a series circuit, right? And I have a parallel circuit. And I have current and voltage. Right? We don't need resistance for this in this case, right? Current in series is the what? Is the current in series? Yes, sum it up or is the same? Same. Current in series stays the same. But voltage in series does split up. Okay, remember that? The voltage here and the voltage here splits up, right? And the current through this and the current through this is the same. What about parallel? Is it opposite, right? It will split up current and the in parallel it will stay the same. Right. So every single time we talk about current, how we can put the charge division? How we will talk about charge? What about charge? What's the difference between current and charge? Right? Aaron said Q is equal to IT. So at a constant time, Q is proportional to I. So Q and I behave the same way, Arian. Right? Q and I behave the same way. Right, Pancho? So I can take off I and I put in Q for now. Okay? They both behave the same way. All right? So, Timothy, here's the problem now. Right? Besides divisional listening, the next problem is we need to get a relationship for C1 and C2. Right? You remember in Form 1 when you prove resistance in series and resistance in parallel? Yeah. Timothy, you remember we did a formula for series resistance in series and resistance in parallel? Can I form 5? Yes, do that. All right. Anyway, when I have my remember. Right? When I have how it is now, we have to get some kind of relationship here for capacitance in series and capacitance in parallel. Well, series, right? We need to get an equation. So we had to use a relationship that we know to help set up that equation. What's the first thing that we could probably start up with here? Q is equal to anybody else?
Q is equal to CD.
Right. We know that, but we can't use it. We can't start with that. What we know about series circuits? I will close there. B is equal to R close. What we know about a series circuit? Always add up.
What resistance?
No have no resistance here.
Oh.
Only voltage adds up, right? So if I have a voltage here V1 and I have a voltage here V2, when I add up V1 and V2, what would I get? V, right? So based on this formula here, Shivish, what is V? Based on this formula here. V is what? That is sign off. What is that? Q over C, right? Q over C. Right? Here Q, right? What we know about charge in series, Vinay? Anthony, what we know about charge in series? It's the same. So the same charge here, same charge here. So right now in series, both capacitors, the potential have the same watts. Oh, you have to be listening and getting the answer right. Right? So they have the same charge, right? So they have the same Q value here, here, and here. So what you say? How do I find V1 then? V1 is Q because it's the same value here over C1. How do I find V2? Q over. That's okay? Huh? Oh, thanks. You're okay with that? What do I do now to make it look nice? And they all have Q, I can cancel up on Q's. So I can divide by Q. And I will get this formula here. This is the formula for capacitance and series. Yeah, you have to learn to write it. This is something what? That is just something what? So this. Right, yeah, so it's similar, yes. But this series is parallel and parallel is series. Right? So you have to be able to prove that. This in your notes. This in your notes, just anyway, you can write it down again. Right, division. Come on the board and I want you to do parallel from a division. Every time I look, you want you talking to Nolia. Come. Okay, all right. You talking to somebody. Come and try this here, division. Come division. Yeah, oh yeah, come pretty quick. Here's some good crumbs there. Very similar to this. Come on, do it fast. Charges, when I show you on this slide, you're doing something. Come quick. Oh yeah, last one. The punch you go to what make you happy? Think real about it, I'm cool about it. But what I'm not man, do stuff talking, you know. Hey, all you have to do is figure out where you're starting with. So watch, what? See, I start here. Voltage splits up in series. What is split up in parallel? Charge. Right. So right, Q is equal to Q1 plus Q2. Q1 plus Q2. Right. What you have to do now is figure out how to find Q. Q is what? Look at the formula here. Q is what? Right up. For each one. One by one. Right, Q is equal to C by V. C by V. Yeah, Q is C by V. Right, and when you reach here, what to do? Cancel out the V. So that's divide by V. And write the answer. Right, so the base model watching now, you do not have a work, right?
Yeah.
Right. What you end up with? Right, but Soraya does, she doesn't do anything in class. Right? You never remember the time? 5 minutes before the class finished. Not telling them where to look. Where exactly what time to look. I'll be like, I'll tell them, I'm gonna tell them where. And which live. Right? You're okay with that? Real simple, right? You just start You just start with this here, parallel system. That's all they're doing. Okay? All right. So that time just reading one.
Let's take a break. So we let's start with that. Let's see, yeah, because we have to do it.
So I give all that. Got it all? I don't put the first now. Alright, so next day we'll take all these little formulas. So watch please. Shivish. 1, 2, 3, 4 formula we learn today. Next week, make sure you know all 4 of them. Right? Yeah, I can do up to question in 5 minutes. Alright, so we reach here. Take the note and I want you to read out the next part of the note, right? And the handout, right?
I think people read off, but they read it from January.
Up.
You
I'm not saying 4 formulas. That will take 5 minutes.